Recapitulating, we have omega is equal to theta by dt, alpha is equal to d omega by dt, alpha also is equal to omega d omega by d theta, alpha also is equal to d square theta by dt square. And theta can be calculated by integrating omega with respect to time. So, these are all the expressions you need to remember. And I will tell you in the next sections how to use all these expressions through several examples. Here I may take a small example for you. For instance, omega is equal to 2t. Angular speed changes in this way. Find the angular distance during first second. During first second, what is the angular distance covered by the body? Angular distance is equal to, or you can just write, angular velocity is equal to d theta by dt. This gives us, by cross multiplication, during a very small time interval dt, this covers a very small angle d theta. So, the total angle covered during time t can be calculated by integrating both sides. At time t equal to 0, let us assume that theta is 0. At time t, you will get the angle theta. So, theta can be written as omega dt integral from 0 to t. This is what is the derivation of this formula. Using this formula, we can substitute omega is 2t and its integral from 0 to t. So, how much you are getting? T square by 2 into 2. This is t square from 0 to t is equal to first second from 0 to 1, that is 1 radian. Answer. So, this is the utility of this formula. Let us use this formula. This formula you can use only theta is given as the function of time. Let us take an example for this. Well, let us take the example for this formula. Suppose theta varies. Theta means you draw this radial line, this angle varies with respect to time like this. Theta is equal to 2 t cube. If, then find angular velocity and angular acceleration at time t equal to 1 second. Differentiate it to get the angular velocity with respect to time t once. 2 into 3 into t square, that is 6t square. At t equal to 1, we get 6 radian per second. Positive means it is outward. Alpha is equal to d omega by dt. Again you differentiate this factor. D by dt, this is equal to 6t square is equal to 12t. at time t is equal to 1, 12 into 1, that is 12 radian per second square, answer. So, this example utilizes this formula or these two formulae, because using these two formulae, putting omega is equal to d theta by dt in the second formula, alpha is equal to d omega by dt, we got alpha is equal to d square theta by dt square. So, you are differentiating theta 2 times with respect to time. Now, let us take an example to use this formula. If alpha is equal to k into omega, if the angular acceleration of a rigid body is directly proportional to the angular velocity, assuming initial angular velocity at time t equal to 0, that is called initial, omega naught is equal to 2 radian per second, k is equal to 1. Find omega at theta is equal to 10 radian. Right, alpha is equal to omega d omega by d theta. This is the formula, one of the formula for angular acceleration, and given angular acceleration condition is k into omega is equal to omega d omega by d theta. Omega will be getting cancelled from both sides to get k into theta by cross multiplication is equal to d omega. Let us integrate both sides. When theta is equal to 0, omega is omega naught. When theta is theta, omega is omega. So, we are getting k theta is equal to omega minus omega naught. What do we want? We want the angle, or we want the angular velocity at theta is equal to 10 radian. This we want. So, keep it in left hand side. Omega is equal to omega naught plus k into theta. What is omega naught? Plus 2. What is k? That is 1 unit. And what is theta? At what theta? 10 radian. How much you are getting? 10 plus 2, that is 12 radian per second, answer. So, these are the basic examples. To just brush up all these formulae, we deduced. These are called general kinematical formulae. So, after understanding the angular velocity, angular acceleration, the angular distance or the displacement, let us go to the next section, where I will be able to, by using all these ideas of angular velocity, which defines the motion, I will be able to describe different types of motion of the rigid objects. Next, we need to calculate the angular acceleration. Before I start the next section, I would like to calculate the angular acceleration by taking one example. Let us recast the previous example of sliding rod. This rod slides under the two constraints, to surfaces which are perpendicular to each other. This is x direction, this is the y direction, this is vertical, this is horizontal. You are pulling the bottom end of the rod with a constant velocity, say for the sake of simplicity. This is the angle, length of the rod is L, and you did this problem to find omega is equal to V by L cos theta. We will solve this problem. Now, how to find alpha? Alpha is equal to, yes, which formula you can use here? We have the formula of alpha, d omega by dt. Another formula is omega d omega by d theta. Since omega is given as the function of theta, these are all constant quantities, we need to use this formula, omega d omega by theta. What is omega? V by L cos theta, then d by d theta by V by L cos theta. V by L cos theta, you take V by L out of the derivative, d by d theta of secant theta. We are getting V square by L square by cos theta. Secant theta derivative is secant theta into tan theta. If you want to convert it to sin or cos, that is possible, or if you want to keep it like this in terms of secant tan also, that's also possible. 1 by cos can be written as secant, so secant square theta tan theta, and so this is the angular acceleration as the function of theta. If you use this formula, also you can get same answer. Alpha is equal to d omega by dt. What is omega? Omega is equal to V by L cos theta. Take V by L out, so d by dt, the secant theta. This can be written as secant theta into tan theta d theta by dt. But we know that d theta by dt is equal to omega. This itself is omega. Secant theta into tan theta into V by L, instead of d by d theta by dt or omega, you can write again V by L cos theta. Are you not getting same answer? You must get same answer. So in this way, you can use all these general kinematical formulae of omega and alpha, angular velocity and angular acceleration. Angular velocity as a function of theta, angular acceleration as a function of angular velocity, angular acceleration as a function of angular velocity and angle. Angular acceleration as a function of, in terms of angular velocity and time. Alpha in terms of omega and t, alpha in terms of omega and theta. Well, all these ideas of the angular quantities like angular displacement, angular velocity, angular acceleration are in front of you now. All these formulae you have derived are on your table. These are called general kinematical equations. Here we should take a pause and try to understand how many types a rigid body can move. For instance, if I release the body, it moves. It moves, but the angle of orientation of this rigid body, the pen, is not changing. While it is moving, the angle of orientation is not changing. If it is not changing its angle of orientation, then we can say that theta is constant. It moves like this. It moves like this. Without changing its angle of orientation, it moves. When the angle of orientation theta does not change, it remains constant. The rate of change of this angle, that is what we call angular velocity, will be equal to 0. When angular velocity will be equal to 0, the body does not rotate. The body is said to be translating. If omega is 0, the body is not rotating. The body is not rotating. For non-rotation, if the body does not rotate, omega must be 0. This is the condition. Yeah. But the center of mass of the body, falls freely, moves with increasing speed with an acceleration g. The center of mass translates, but the center of mass moves. If velocity of the center of mass is not equal to 0, the body is said to be translating. So what is rotation? The fundamental concept of rotation is non-zero angular velocity. The fundamental concept of translation is velocity of center of mass, not any point's velocity, only center of mass velocity of the rigid body. That velocity is not equal to 0. So when the body rotates without translation, omega is non-zero, but center mass velocity is 0. I will tell you through an example. Suppose this example, and this example I gave, freely falling rod, is freely falling. It's not the case of rotation, because this angle is not changing. That is pure translation. That is called pure translation. In pure translation, each point has same velocity of the rod, of the rigid body. Each point moves with same linear velocity, omega 0. Then the body is said to be translating perfectly. Hence, V1 is equal to V2 is equal to V3 and so on. All these points move with same velocity. Linear velocities of all the points of the body are equal at an instant. Then the body is said to be translating perfectly, and the angular velocity of the body will be exactly equal to 0. That is the clear-cut case of pure translation. So, through an example, this is the first type of motion of the rigid body called pure translation. Next, I pin the center of mass of the disc. When I pin it, the center of mass velocity will be equal to 0, and then I spin, give a spin. I rotate it with omega. Here omega not 0, but Vc 0. This comes under which category? When Vc is equal to 0, then the body does not translate. Hence, the rigid body rotates perfectly. A pure rotation pure, or better to say fixed axis rotation, the axis is fixed. Fixed axis rotation, the second type of motion of the rigid body. Fixed axis rotation, for instance, our ceiling fan or table fan, they are fixed axis rotation because the center mass doesn't move, while the angular velocity is not zero, the RPM of the blades are not zero. Then we will talk about the third type of motion of the rigid body. In pure rotation, let me ask a basic question. I take this radial line, I take some arbitrary lines, line 1, line 2, line 3, line 4, line 5. If the line moves with an angular velocity omega 1, this line moves with an angular velocity omega 2, this line moves with an angular velocity omega 3, this line rotates with an angular velocity omega 4, this line rotates with an angular velocity omega 5. How they are related? How their angular velocities are related? This is a common sense basic question or conceptual question. As I told you, all lines are fixed with respect to each other. Therefore, when one line rotates through an angle d theta, all the lines will change their angular orientation by same amount in same direction. Therefore, the angular velocities of all the lines, straight lines, must be equal to each other. Omega 1 will be equal to omega 2, will be equal to omega 3, will be equal to omega 4, and so on. And that is defined as the angular velocity of the rigid body. That's the property of the body. It doesn't depend upon any straight line outside or inside. It doesn't depend upon any reference point or reference axis, as I discussed previously. Well, this is the fixed axis rotation, a pure rotation so called. In this case, all particles are moving in circular paths. This particle moves in this circle, this particle 1 moves in this circle 1, and here the particle 2 moves in this circle, here the particle 3 moves in this circle. All the particles are moving in circular paths. In fixed axis rotation, any particle or any point of the rigid body moves in circular paths. Only in fixed axis rotation. Therefore, it may give some wrong impression that rotation means circular motion. Therefore, it may give a wrong impression that rotation means circular motion. For fixed axis rotation only, all particles will move in circular path. But reverse may not be true. Reverse may not be true. Circular motion, rectilinear motion, parabolic motion, elliptical motion, all types of motion along a line. This line can be curved line, that line can be straight line. Motion along a line is attributed to a particle or a point. However, rotational motion is attributed to a straight line. Many straight lines can be drawn inside the rigid body. Therefore, rotation is attributed to the rigid body or a straight line at least, and translation is attributed to a point mass or a point or a particle. Therefore, you should not get confused that rotation means circular motion. For fixed axis rotation, all points move in circular paths, but reverse may not be true. When a point moves in a circular path, the point is not at all rotating. Then what are the terms you can use for this? You can use the term revolution. That's a better term. The particles or the points are revolving in circular path, but they are not rotating. Rotation word cannot be used for the points or the particles or the point mass. So in fixed axis rotation, linear velocity of any particle P can be given as r into omega, because this particle moves in a circular path. Using the concept of circular motion, this particle velocity is tangential to the circle and is equal to r into omega. Everybody knows this in circular motion kinematics. So different particles will move with different velocities with respect to the axis O. However, angular velocity of this particle with respect to O will be equal to omega. Angular velocity of any other particle Q with respect to O will be equal to omega, because this straight line, these straight lines, all straight lines drawn inside the rigid body, in this case, must move with same angular velocity. However, these points, different points will move with different velocities. This point is further from the axis. Therefore, it will move with more speed. It will move faster. Vq is equal to, this is r phi, Vq equal to rq into omega. R phi, since rq is greater than r phi, this distance is greater than this radial distance. Therefore, and omega q with respect to O is equal to omega p with respect to O will be equal to omega. Definitely, velocity of this point Q is definitely greater than the velocity of this point P. So, the points which are farther from the axis will move more rapidly. That's the point here for pure or fixed axis rotation. These are some special type of rotation when the axis or axle is fixed, like pedestal fan, the ceiling fan, etc. There is another type of rotation. For example, this cricket ball, or this is a disc. You spin it like this and leave. When you spin it and leave, its center mass moves. Therefore, the velocity of center mass is not equal to 0. At the same time, the body moves with some angular velocity. When you spin it and leave, spin the ball in this way and leave, its center of mass moves. So velocity of center of mass is not equal to 0 and angular velocity of the rigid body is not equal to 0. This plus this. So angular velocity not 0, therefore it is rotating. And center of mass velocity is not 0, therefore it is translating. So it is rotating plus translating. That is therefore that's called combined motion. This is third type of motion of the rigid body. Combined motion. The rigid body rotates, possessing a non-zero omega. The rigid body translates, possessing a non-zero velocity of the center of mass. As I am displaying, when I spin it, it rotates because the angle of orientation of this pen keeps on changing. Therefore, it has non-zero omega. And the center of mass, this center of mass also moves. Therefore, this is a clear-cut case of combined motion. And this is a clear-cut case of, let us discuss. This example, when you pivot it and leave, this body spins, rotates with omega. But the center of mass, when this axis is fixed, all the points move in circular path of the common center, that is the pivot here. And all the points are having same angular velocity with respect to this pivot. Since velocity of the center of mass, midpoint of the uniform rod, is not equal to 0, this is translating. And since omega is not equal to 0, this is rotating. Therefore, this is a clear-cut case of combined motion, but sometimes it gives the wrong impression that this is pure rotation. It's not pure rotation. Pure rotation, it may be fixed axis rotation, but not pure rotation. Now we can rectify this concept, or we can clarify, or we can separate these two concepts. These two concepts are pure rotation and fixed axis rotation. In this rotation, the axis must be fixed. But pure rotation is that when velocity of center of mass is equal to 0, it is not translating, only omega is not equal to 0. This is called pure rotation. So pure rotation is different. Fixed axis rotation is different. This may be a fixed axis rotation, but it's not the pure rotation. Pure rotation is also fixed axis rotation. But all fixed axis rotation are not pure axis rotation, pure rotation. For instance, this is the center of mass. We pivot it like this. And here we pivot it like this. Here center of mass velocity, since it is pivoted, is 0. And we can spin it. Omega is not equal to 0, therefore it is a rotation or rotating. And this is no translation. No translation for rotation is called pure rotation, only rotation. And here it may have non-zero omega, but it must have, this is center of mass, will possess a non-zero speed which is equal to L/2 into omega is not equal to 0. Therefore, it has translation or translating motion or translatory motion, and it has a rotation also. Since omega is not 0, this rod is rotating. Since the velocity of its center of mass is not equal to 0, this is translating. So therefore, the rod is undergoing both translation and rotation, even though this axis is fixed, even though this is fixed axis rotation. Both are the examples of fixed axis rotation, but here a combined motion, rotation plus translation. And this example A, here only a rotation, no translation, no translation, or pure rotation. There is a clear-cut case of pure rotation. This is called combined motion. Sometimes we can call it non-centroidal motion. This is called centroidal motion also. But I don't want to use all these terms. We have to use the easy terms to understand what is pure rotation, what is fixed axis rotation, what is pure translation, what is combined motion. With all these ideas, we have to proceed to explain the concept of rotation based upon the assumption that the rigid body is a flat or plane-like structure in general. It should rotate in the plane of the board without changing the axis of rotation or without changing the direction of omega. For instance, a spinning disk. This disk spins. This is the disk spinning. Center of mass moves, both omega non-zero and velocity of center of mass non-zero. Combined motion, but it is not changing the plane. It is moving in xy plane. So we have to restrict our discussion of rotation in a single plane. And using all these ideas, in the next class, I will reduce the expressions for uniformly accelerated motion in rotation, that is possible only when the body will possess a uniform or a constant or an unchanged angular acceleration, and that particular concept is called uniformly accelerated motion. Just like in our linear case in translation, when you leave this body, this comes down, its center of mass moves with uniform acceleration. Therefore, this translatory motion is a uniformly accelerated motion. Similarly, when a body rotates with a uniform angular acceleration, that is also called uniformly accelerated motion, but that motion is rotational motion or angular motion. In next class, we will talk about uniformly accelerating angular motion or uniform angular acceleration. The body is undergoing uniform angular motion, will be having the angular velocity, the angular displacement with respect to time. We will deduce the expression for them, just like the linear case in uniformly accelerated motion, s equal to ud plus half at square, v square equal to u square plus 2as, v equal to u plus at. Similar set of equations in angular motion or rotation we need to develop in the next class. like omega is equal to omega naught plus alpha t, omega square minus omega naught square equal to alpha into theta, theta equal to omega naught t plus half alpha t square, and so on. So this basic understanding of the different types of motion are ultimately required for our further analysis.